Chapter 2.7 Energy Resources 2.7.1 Predictions. As mechanization spreads globally, open field intensive agriculture increasingly relies heavily on fossil fuels to power farm machinery and for transportation of fertilizers as well as farm products, as well as to run equipment for processing, packaging, and storage. In 2010, the OECD International Energy Agency predicted that global energy consumption would grow by up to 50% by 2035. The FAO has also estimated that 30% of global energy consumption is devoted to food production and its supply chain. FAO 2011. Greenhouse gas emissions associated with fossil fuels, approximately 14% in life cycle analysis, added to those from fertilizer manufacturing, 16%, and nitrous oxide from average soils, 44%, Camargo et al. 2013, all contribute substantially to the environmental impacts of farming. A trend in the 21st century to produce crop-based biofuels, for example corn for ethanol, to replace fossil fuels has increased pressure on the clearing of rainforests, peatlands, savannas, and grasslands for agricultural production. However, studies point to creation of a carbon debt from such practices, since the overall release of CO2 exceeds the reductions in greenhouse gases they provide by displacing fossil fuels. Fargione et al. 2008. Arguably, a similar carbon debt exists when clearing land to raise food crops via conventional agriculture that relies on fossil fuels. In a comparative analysis of agricultural production systems, trawling fisheries and recirculating aquaculture systems were found to emit greenhouse gases 2 to 2.5 times that of non-trawling fisheries and non-RAS, for example, pen and raceway aquaculture. In RAS, these energy requirements relate primarily to the functioning of pumps and filters. Michael and David, 2017. Similarly, greenhouse production systems can emit up to 3 times more greenhouse gases than open field crop production if energy is required to maintain heat and light within optimal ranges. However, these greenhouse gas figures do not take into account other environmental impacts of non-RAS systems, such as eutrophication or potential pathogen transfers to wild stocks. Nor do they consider greenhouse gas from the production, transportation, and application of herbicides and pesticides used in open field cultivation, nor methane and nitrous oxide from associated livestock production, both of which have a 100-year greenhouse warming potential, 25 to 298 times that of CO2, respectively. Camargo et al. 2013, Eggleston et al. 2006. These sobering estimates of present and future energy consumption and greenhouse gas emissions associated with food production have prompted new modeling approaches. For example, the UN's Water Food Energy Nexus approach mentioned in Section 2.1. The UN's Sustainable Development Goals have pinpointed the vulnerability of food production to fluctuations in energy prices as a key driver of food insecurity. This has prompted efforts to make agri-food systems energy smart, with an emphasis on improving energy efficiencies, increasing use of renewable energy sources, and encouraging integration of food and energy production. FAO 2011.